Voici quatre séquences,
We
quatre
present here 4 videos with numerical simulations illustrating the time evolution of an isolated, self-gravitating system of particles. In other words, only influenced by its own gravitational force. In the following simulations, we used a limited number of particles, 8,000 particles, shown in the upper part of the simulation with an enlargement in the right part of the simulation. At each instant between each video frame, all the gravitational forces between the particles are computed in order to predict at each time the position and the velocity of each particle, and to let evolve with time several quantities such as the viral, the kinetic energy, the potential energy, and the total energy. Let's evolve the system over time. In each following footage, the initial positions of all the particles are strictly the same. Only the velocities, that is the kinetic energy, changes. In each simulation, we show in the bottom part of the video the kinetic energy in green, the potential energy in red, and their sum, the total energy, in white. As for the viral, i.e. twice the kinetic energy plus the potential energy, it is shown in blue. We first see that in such a system, completely isolated, that the total energy is always exactly conserved, up to numerical errors, up to the accuracy of the simulation. The potential energy, plus twice the kinetic energy, namely the viral, oscillates indeed around zero over time. Let's see what happens now if the system is not isolated anymore. We introduce an external perturbation to the system, which affects the shape of the self-gravitating system, which actually isn't self-gravitating anymore, and affects the physical quantities we measure. The physical quantities are in the lower part, and the system still in the upper part. We see that under the effect of an external perturbation, the system deforms over time, and we also see that the total energy increases. The viral does not oscillate around zero anymore, but also tends to increase. In this specific case, we tend to add up kinetic energy to the system through the external perturbation. Now let us go back to an isolated system that is without external gravitational field anymore. We will set initial conditions such that the kinetic energy is too low to counterbalance the potential energy. In such a case, the total energy is, of course, conserved over time, since the system is isolated. What happens is that the system has to contract to make a sudden increase of the kinetic energy at the beginning of the simulation. In order to gain kinetic energy, we lose potential energy, and to lose potential energy, the system contracts until reaching an equilibrium after a some time where the viral oscillates around zero. The system was initially too big for its kinetic energy, and, as such, contracted itself to reach a new equilibrium. In a similar way, if we take an isolated system, but this time with too much kinetic energy, in regards to potential energy, then the kinetic and potential energies will balance each other. As seen here, the kinetic energy decreases over time. The potential energy increases over time. The total energy is conserved, since the system is isolated, and the viral will naturally converge to a mean value of zero after a some time. As opposed to the previous simulation, the system will grow in size, contrary to the contraction observed previously. The numerical simulations shown here only use a limited number of particles, yet enough to illustrate the time evolution of a self-gravitating system. However, they only take into account the gravitational forces between the particles. Other numerical simulations can be used to understand the formations and evolution of galaxies. They can include up to hundreds of billions of particles, as well as the physics of gas surrounding the particles, and the explosion of supernovae. In the simulation you see behind me, we use 10 million particles to model the evolution of a spiral galaxy over several hundreds of millions of years.